everyone. Welcome back. Happy Monday. So, oh, all right. So, last lecture we went over isoplething a little bit, and I kind of talked about the details of that. I didn't make a example video because I'm not going to expect you to do that on a quiz or a test, but it is important. So, if you don't really understand how isoplething works, feel free to contact me or to watch some extra videos on YouTube. It's pretty easy. And then we talked about converting from UTC to Central Time, Standard and Daylight. So for Standard Time, it's a 6-hour difference, and Daylight Time, it's a 5-hour difference. So today we're going to get into something a little more interesting, in my opinion. We're going to talk about upper air maps. The upper atmosphere is really the driver of the severe weather events we have in the United States. Whenever I'm like looking for severe weather, the first thing I always check is the 300 millibar heights map, and I use Pivotal Weather. So you just go onto Pivotal Weather, and then you click the 300 millibar heights, and you can see all the features that we're going to talk about today. Can you hear my cat meowing? He does not like when I kick him out, but he cannot stand me teaching lectures. Okay, let's talk about upper air observations. Let's give a brief overview. So, upper air observations are measurements of the atmospheric properties above the surface. So, this is up pretty good in the top of the troposphere. Like, you really get up there. And the ways that we get these measurements are weather balloons, pilot reports, radar, and satellite data. And weather balloons are released every 12 hours, so that's about how often upper air maps are updated. I usually check I think it's 0Z and 12Z is when these launches are valid. So whenever I'm looking at a model like the GFS, these long-term models, I will look at it at 0Z or 12Z for the run, because whenever you go out past these times, it's more interpolated. So it's the model saying, I'm going to make a calculation about what I think is going to happen, and that's going to be the new data. But at 0Z and 12Z, the data is raw, the data is fresh, and it, in my opinion, it gives the most accurate forecast. Now, a model like the HRRR, which stands for High Resolution Rapid Refresh, or NAM 3 kilometer, these are called convective allowing models. These models are designed to find convection, and usually I will use these on the hour, so I don't really look at just the 12Z and the 0Z, but on a model like the GFS, when I'm looking for a forecast that's farther out into the future, I will use the 12Z and 0Z. Okay, so remember this diagram. We talked about it a little bit. So this is the x-axis, and it's just the temperature in Fahrenheit, and the y-axis is the height above the ground. And we focused on using height as the vertical coordinate in soundings, but as I've said before, we usually use something different, and for upper air maps, this is something that we will use, and it's what's used on the weather model websites. So we use pressure coordinates. So atmospheric pressure always decreases with increasing height above the ground. So that means that every altitude above Earth's surface has a unique value of pressure. So pressure is used as the vertical coordinate on upper air maps. And the lower the value of the pressure level, the higher up above the ground it is. So, for instance, like at the surface, you'll look at like a 1,000 millibar map or something like that, and then when you're looking at the upper atmosphere, I usually look at like 300 millibars. And sometimes in the summer, you can look at 200 millibars. So, yeah, the upper atmosphere has lower pressure. The middle of the atmosphere is usually around like 500 millibars. And then, like for the low level features like fronts and whatnot, you could use like a 925, 800 millibars, or even 750 or whatever they use. Okay, so we use certain standard pressure levels to make upper air maps. So like the ones I just listed, we have like a group of levels that we use. And basically the map is a connected, it like connects all the points where there's the same pressure. So it's not like a straight line across the sky. It's going to have like tilts in it because the pressure levels will be at different heights. But they're all roughly around the same area. And we can use those height values to make determinations about the weather in the atmosphere, like the height of a certain pressure level. So it's a surface of constant pressure. And the standard pressure levels are chosen because they're most helpful when looking at certain weather features. So let's talk about some of them. Let's start at the surface. Usually when I'm looking at a weather map, though, like I said, I'll start at the top of the atmosphere and go down. But for this, I'll just start at the surface. So let's talk about P naught here. So they picked for their P naught to be 850. So this is, you know, about 1.5 miles above the surface, but it depends on where you are. Like if you live in Colorado, your surface is at 850 millibars. So, and this means that 850 millibars of pressure remain above this level. So this is about the top of the boundary layer, and it's the best, I wouldn't call it an upper air map, but it's the best map for looking at fronts, dry lines, and the low-level jet. So fronts, dry lines, and the low-level jet are all considered surface features. So you're going to look in the lower atmosphere to find like these phenomena. Moving up, we have 500 millibars, which is about the halfway point. It's 5.5 kilometers above the ground, roughly. And this is the middle of the troposphere. Yeah, this is like the center. And this is the air map for locating high and low height centers, ridges, and troughs. I guess. I usually look for ridges and troughs at 300 millibars. Maybe this person who made this PowerPoint thinks differently than me. Usually when I look at a 500 millibar map, I'm looking for vorticity. And you'll probably get into this, you definitely will get into this in your future meteorology classes because it's very important. But vorticity just means spin. It means how a molecule wants to rotate at a specific point in space. So it's like a energy measure. So I usually look at 500 millibar vorticity. They didn't include like the 700 millibars or whatever. Usually I look at moisture profiles at 700. I can't remember if it's 700 or 750, but it's in the 7. I think it's 700. Yeah, that's it. That's good for finding the moisture profiles. So, yeah. Maybe I'll make a video about using weather maps, and I'll say my opinions on the best way to use them. So then let's go to the top of the atmosphere, 300 millibars. So this means that only 300 millibars of pressure remain above this level. So the height is around 9 kilometers. So this is about the pressure at like Mount Everest. Like it's hard to breathe up there. And this is about the top of the troposphere. And this is the best upper air map for locating the polar and subtropical jets. So yeah, in my opinion, like the ridges and troughs are the polar and subtropical jets, so that's why I look for both of them in this upper level. So this is in the middle of the atmosphere. This is 500 millibars. And we can see by these numbers here. So this was taken on December 19th, 2018 at 0Z, so 0 UTC. So if that we would subtract 6 hours from that, and that would make it 6 p.m. So upper air maps look a lot like surface maps, but the numbers and shading for each station are decoded differently. And we're not going to do that, but we will look at the wind barbs. So upper air maps are made from observations taken at the standard pressure levels. We already said that. So that means that the pressure is constant everywhere on this map. So everywhere on this map, the pressure is the same. So they're called constant pressure maps. And you can see these values right here. These are heights in meters above the ground. I think maybe it's meters above sea level. That would make most sense in my opinion. So yeah, like for instance here, I'm assuming this is a low because it's within a trough and it's closed off. It's 5,040 meters above sea level. But over here, the same pressure level, so this is 500 hectopascals. This over here is also 500 hectopascals, but this one is 5,700 feet above sea level. So it's lower in the atmosphere up here than it is up here. It's like this is kind of like a literal bubble of air where the atmosphere is higher, the same pressure level is higher over here than it is over here. So where's the high pressure center? I kind of pointed it out. I think it's over here. We'll find out. Oh, I got fooled. They tricked me. But yeah, I was thinking about the surface. But yeah, trick question. The pressure is the same everywhere on this map. So, isohypes. I'm going to go with isohypes. So that's a line of constant height above the ground. But because height is not constant on a constant pressure surface, we have to have these lines of constant height. This whole thing is the same pressure though. So different heights, same pressure. So this here is closed isobars. So isobars, the line of constant pressure. So on a surface map that have decreasing values towards the middle indicate a low pressure. So I guess that's over here is the low pressure. They put a nice L. But over here is the high pressure. But these values here, I guess these are pressure values and they're just relative. So there's also a low pressure here. So this is a low relative to the air around it. So the pressure here is lower than all the air around it, and the pressure here is higher compared to all the air around it. So these are isobars. These are isohypses. Isohypses. On an upper air map, they have decreasing values towards the middle indicate a low height center. Okay, yeah, so as you can see, the values decrease as you go down, so the height of this pressure level is lower in the middle here. Okay, let's imagine a constant pressure surface like the one to the right. So this one, So this is the pressure line. So everywhere along this line, the pressure is the same. At point A, you have low heights. So this is an area where heights are lower. At point B, you have high heights. So the height of the pressure level is higher up in the air. So let's focus on a constant altitude. So we'll just take an H value across. The pressure is going to change as you go across the height surface. So at point A, the height line is above the line of constant pressure. And we know that the pressure decreases as you go up in the atmosphere. So at this altitude here, there's lower pressure. So if you have low heights, you have lower pressure above that area. Yeah, but if you have a height line of this same pressure and it goes above this, sorry, let me rephrase. So if you have this pressure line and it goes above this constant height line, that means that there is a high pressure at this altitude at H. So there's a low here and there's a high here at this height. So this is why at a region of high heights on a constant pressure map, it's analogous to a region of high pressure on a constant height map. Right. So high pressure is equal to higher heights. Low pressure is equal to lower heights. So yeah, you can see this is what we looked at earlier. So on this one, there's lower heights in the middle. So it's associated with a low pressure. And this low pressure is more associated with storms. Yeah. So we have a low height center and a high height center. So as you go towards this way, the heights increase. So you have a higher pressure down here and a lower pressure over here. So rising and sinking motions cause the high and low pressure centers we see on the surface weather maps. So what causes the height of a constant pressure surface to change and gives us high and low height centers on the upper air maps? And the answer is temperature. So if you have warmer temperature, the molecules will be moving around faster and they'll take up more space, and so the pressure will be greater. But if you have cooler temperatures coming through, you're going to have less of that particle motion. It's not going to be like pushing up on the edges, and so it will shrink. And so you'll have a lower pressure. Okay, that's the end of the first PowerPoint. Let's go to the next one. So we just talked about the upper air maps a little bit. We talked about how they're always plotted on constant pressure surfaces, and the surface maps are on a constant height, and we plot the isobars, so it's the opposite. We just use constant height and we plot the pressures on the surface. But in the upper air maps, we have a constant pressure and we plot the isohypses. So we are plotting lines of constant height. And there's a direct relationship between high and low height centers and high and low pressures on constant height maps. So let's talk about atmospheric thickness. So the thickness of the atmosphere depends on the temperature, and there's an equation you'll use in the future for this. It's called the hypsometric equation. It's a pretty simple equation, but it just directly relates the height of the atmosphere, the thickness of the atmosphere, and temperature. So the higher temperature you go, the thicker the atmosphere is. So if you think about a column of air above the ground and a pressure level P1 in that column of air, So there's 10 molecules below, 10 above. If the column is cold, the air kind of contracts. So these molecules aren't bouncing around really fast. They're kind of like, they're more like a solid, you know, like how when you have a lower energy state, the molecules aren't moving so fast. They're in a lower energy state when there's less heat. So they're just not, they're still a gas, but you know, they're not moving as fast. But if they're warm, they have a lot of energy to move. And so we have higher heights because they kind of like they push each other around and they like expand this height level. So on a warm surface, the pressure level will increase in height. So the height of a given pressure level above the ground depends on temperature of the column below it. So yeah, it's not the temperature above it that matters. It's the temperature below it. So cold air has low heights. It's also, if you think about it, like cold air doesn't really want to rise. It kind of is fine staying where it is. So it's not going to push this pressure level up. But if you have warm air, it's going to want to rise. So it's going to push the pressure level up. So cold air is low heights. Warm air is high heights. Yeah, the pressure surface is definitely not flat. So this is kind of like the line we had before of the constant pressure surface. It's going to look more like this. So the pressure surface changes height above the ground depending on the column of air below it. And the entire atmosphere is wavy, like such. And there's a typical height of each pressure level, but it can vary pretty significantly from that value. That's just like a mean. More thickness maps. So there is like a distinct difference in the heights on the Earth. There's like a better photo to look at this, but if you really think about it, like the heights at the poles, like the atmosphere is like smaller, whereas at the equator the atmosphere extends out further into space just because there's like more thickness because the temperature is warmer. So it's thickest around the equator and it's thinnest around the poles. And the day-to-day atmospheric conditions, like the weather variations, will change the thickness relative to the mean state. So like, for instance, in the summer, it's going to be thicker in one hemisphere than it is in the other, but it's always going to be thicker around the equator than it is at the poles. Ridges and troughs, the bread and butter of meteorology. So a trough is a dip or a valley in these lines of constant height. So that's why like troughs can create low pressures. So they're elongated areas of deep cold air that create low heights, and the heights decrease in the horizontal into the center of the trough. So think about it. So it's pulling this air. This is how the air current is flowing. It's flowing from west to the east. And it's flowing from kind of like this continental polar region into this maritime tropical air mass. So it's pulling this air mass down, the continental polar air mass down into the maritime tropical. So when you have a trough like this, you can really start getting these two significantly opposing air masses to meet. But what happens is that the heights begin to decrease into the horizontal, into the center of the trough. So you have like heights that are decreased up until this point. So you can think of this, it's not only pulling air south, think of it more like 3D. Like you have like this, it's like, it's higher up here and it's lower down here. So whenever I look at these, I don't just see like a 2D flat image. I think of it like a 3D literal trough in the atmosphere. And the same goes for a ridge. So a ridge is more associated with high pressure systems. So it's deep, warm air that creates high heights. And they increase in the horizontal to the center of the ridge. So you literally just have this mountain of air that is highest at the peak of the ridge. And it's like, it's steadily increasing. But it's also got this shape in the horizontal. So it's kind of like these waves that are both in the vertical and in the horizontal. So troughs and ridges are usually strongest in the middle of the troposphere. Questionable, but okay. What pressure level are they best seen on? I guess you can sometimes. I'm going to give that a fat sometimes. So the trough axis is, I usually look for troughs and ridges at 300 millibars. And the reason why is because that's where the wind speeds are the fastest. So you can really like see that jet core up in the upper atmosphere. I guess you can say that the ridges are strongest, but that's only in certain places. Like, I guess, like, with a trough, you might be able to see it better on the 500 millibars because you have it dipping down. Ridges, I don't know. I'm going to continue looking at 300 millibars for ridges and troughs, and I think I will make a video about weather maps and looking at them so we can really see it for ourselves. But yeah, you can see it on both. You can see ridges and troughs on both. Once you get closer to the surface, you can't see the ridges and troughs anymore. But in the upper atmosphere, you definitely can see these features. So the trough axis is the line that connects the dipping isohypes. Yeah, so it helps us visualize the graphic extent of the trough. So, like, you take the point where it's, like, lowest, and you just draw a line through it. So you just draw a line through this, like, local minima, and you can find the axis of the trough. Likewise, you can do it for a ridge, so you just find the local maxima, and you draw the line through all of them. So, and this is, like, kind of, like, helps us see where the ridge is like strongest. So low heights are in the center of the trough and high heights are in the center of the ridge. Yeah, so just remember it's dipping down here in this trough axis and then it's increasing in height in the ridge axis. Troughs indicate a large area of cold air aloft. Yeah, so like I was saying, this is pulling in this cold polar air mass, and it creates an unstable environment. It's because it's digging down, like it's pulling in a cold front, basically. It's digging down into this maritime tropical air mass. So they're characterized by cloudy, rainy, and stormy weather, just because this air is like, you can see that it's low, like the air is low to the ground, so it's gonna push the air up more. Like it's got like, it's kind of like the edge of it and it's like pushing it up, like, yeah. And then ridges, they indicate a lot of warm air aloft, so it creates a stable environment. Like if you have warm air aloft, air is not going to want to rise because air would prefer to rise in an environment that's colder around it. But if you have warm air in the upper atmosphere, the air below it is going to be stable. And they're characterized by calm, clear, and dry weather. And they're also persistent. Like if it's hot in the summer and you get this ridge, like it can stay there for weeks. And that's what's been happening to us. And the National Weather Service is saying like the high this week is going to reach like 108. Weather app on iPhone says 111. It could really be either way, but anyway, be careful outside this week because that is really hot. So, troughs and ridges. So, ridges and troughs, they can cover up to about they can cover several thousand miles. I would say 1,000 miles is about right, maybe a little less. It just depends on how steep your ridge and trough is. But it can tell you what the weather's going to be like over large geographic regions. So these ridges are usually connected to a high height center, and troughs are usually connected to a low height center. Not always. I guess. Usually, like, very much for the most part. Like, I would say, like, I'm not going to give a numerical value because it's unscientific, but I have not seen them not connected to a high and low center in my days. How many years have I been in school? I'm going on my 8th year, and I have not seen it. So, yeah, I would say ridge, high pressure, trough, low pressure, vast majority of the time. Yeah. So, yeah, this low pressure here, so you can see this trough area right here. You can imagine that over in this area here, you're going to get a lot of storms. While over here in this area where you have this ridge, you're going to not see much dramatic weather. It's just going to be clear skies. Small troughs, these are awesome. So these tiny little troughs, they're like embedded within the flow. So you have like this main flow here. This is a ridge overall, but within it, you have these little mini troughs embedded within it. So, yeah, and this is a vorticity map. So this means spin. This is what I was talking about earlier. So you can see in these things, you can get a lot of spin. These short waves are powerful because you have to get air flowing super fast around these to catch up with the air that's not having to go around these short waves. So with it, you get all this extra juice to form these storms. So, yeah, if you're looking at a map and you see these little mini troughs embedded in it, there's a good chance that it's going to fire up some powerful storms if you have all the ingredients you need. Troughs and ridges, are they going to make a point? I guess they are. Yeah, trough, ridge, trough. So a trough looks like a smile and a ridge looks like a frown. So, yes, dashed line is a trough, and then you have a little mini ridge here. And then you have a big ridge right here. And then you have a little mini trough right here, and then you have a big trough right here. So yeah, this looks like a springtime typical pattern. I guess this is December. Really, anytime that's not the summer, you can get severe weather forming in the United States. Anytime that's not the summer. I mean, I guess if you live up in the north, you can get severe weather, but I've never really lived up here, so I don't know firsthand. But yeah, in Oklahoma, summertime kind of flops. So here is some ovals. This indicates, rising motion. So we're going to revisit this, I guess, but on this side of the trough, like it's on the rising motion you mainly get is on the right hand side of the trough axis. So it's not going into the trough, it's exiting the trough, where you really get to see this upper level divergence. It creates a vacuum aloft and air is kind of sucked up. You get a lot of rising motion on the right hand side of the trough. This is where the severe weather is going to happen. I'm not going to point to this California area because usually you don't have like the different air mass structures to support severe weather in this region. You can up here in like the Montana area and stuff, but once you pass over the Rockies, you can really get some interesting stuff going on. And yeah, so I would say the Carolinas and all the way up the eastern seaboard is gonna get severe weather in this instance. Okay, the final PowerPoint for the day. So we just talked about thickness. If there's a warm layer below, you get higher heights, and if there's a cool layer below, you get low heights. And then we just discussed troughs and ridges. I'm sorry, I do not watch The Office. I watch anime. I'm really sorry. But I hope that you enjoy this meme. So what upper air map is the best? 300 millibars, jet stream, yes. Because the polar and subtropical jets occur at the top of the troposphere, 300 millibar is close to the top of the troposphere. Yeah, so this is good for viewing the jet stream. In my opinion, the jet stream is what forms the ridges and troughs. So this is why I like looking at this feature, this 300 millibar map, to find ridges and troughs. Moisture and moisture advection, 850. Sometimes 700 even. If you can get a good moisture profile at 700 millibars, like that is really prime time for severe weather setup. But you don't necessarily need that. If you have enough moisture at 850, you can really get some rising motion. So yeah, look at the 850 millibar maps, look at the dew points, and you can really, the isodrosotherms. They're lines of constant dew point. And they're usually shaded, so you can, I don't know why they picked this map, because it's all the way down here. But yeah, like over here, in the Puerto Rico, Cuba, Dominican Republic area, you've got some good moisture up there. But you can get this moisture pulled up into the United States, like the moisture tongue, you can really get some moisture up in there. So, yeah, 850, we talked about it, is kind of like the top of the boundary layer. So this means that there's moisture at the top of the boundary layer, which is good. It means that you have a nice setup to get rising motion. It's good, in my opinion, and many other meteorologists' opinion, it's good to also have some surface moisture. So don't let, just because you have like a moist 850 profile, if you have a dry surface and a cool surface, that's no good. So you want like a thick moisture layer. Like you want there to be some surface moisture to get the conditions for the air parcel setup. And you want the surface to be warm enough to get rising motion as well. But if you have 850 millibar moisture, you're probably going to have some surface moisture as well. Just check every layer. Don't just look at one layer, like look at all of them. Dry lines as well, you also can look at 850. So this shows the lines of constant dew point. It's similar, so you just look for the boundary between the warm and dry and warm and moist air masses. So if you see the air suddenly turn very dry, this map, I do not like these. I know it came out of the Storm Prediction Center, and that's at our school. And the Storm Prediction Center is awesome, and they're doing the Lord's work. And their website's amazing for figuring out where severe weather is going to be. But this map is ugly. This is like a sneeze on a screen. So usually you can find a better map of moisture that's more shaded, and you can really see the gradient. Like some of the Oklahoma Mesonet maps we looked at earlier, you can find dew point maps that look like that online as well, and you can really see where these dry lines are going to form. Long story short, you can see these dry lines at 850. The low-level jet, we talked about this earlier. It's that nocturnal feature that pulls air from the Gulf towards the north, towards Oklahoma at night. It's at night, so it's this like strong jet that points north, and it pulls the moist air into our region. Lucky us. So if you look at 850 and you see these strong southerly winds, so you can see these wind barbs here, and they're pulling this air north, and you can see the high dew point values being affected by these winds, so it's pushing these dew point values north. You probably have a low level jet. You can also look at the time of the sounding, 21, so 7 p.m. In my opinion, that's 7 p.m. I don't know if, yeah, it's 7 p.m. So the sun's kind of set at this point, and that's after sunset. You can get the low-level jet start to form. Good. So that's the low-level jet, confirmed in every way. Fronts, also 850. You can also look at the surface, but sometimes surface heating is weird. So you can look at 850, and fronts run kind of deep. Like they're at the surface, but they go up into the atmosphere. So they're not just at the surface. Like the air masses have an upwards volume. So 850 is close enough to the surface to pick up on these fronts. If the isotherms are plotted on an 850 millibar map, you can use them to locate the fronts. So remember, isotherms are lines of constant temperature. So the fronts are located at the leading edge of the temperature gradient on the surface maps, and the wind direction is used to determine the front type. Yeah, so we kind of talked about this. So in my opinion, I see the biggest wind shift like over Oklahoma. Like you really see these winds starting to turn around. So I think right here, like through Oklahoma, like eastern Oklahoma, eastern Texas, even eastern Kansas, I think that's where the cold front is. And I guess I can try to see the temperature. These temperatures are really hard to read. Yeah, I guess it like over here you have temperature like 16, 18, and then over here you have 0, -5, -12. So that kind of like proves the point that these temperatures kind of drop off dramatically where these wind shifts occur. And this is an 850 millibar map, so it's good for seeing that on there. You can see it on there. Didn't we just see the slide? Oh, okay. Look, okay, they drew it for us. Yeah, so right where I was saying, yeah. This is the cold front. And this is the warm front. So you have these southerly winds pushing up this warm air. And the temperatures start to increase. So you have like this edge, like the temperatures are decreased up here. So it's like a cool region, a cold region. But on the edge of that, you have these warmer temperatures where it's like 10 degrees, 16 degrees, 17 degrees. Yeah, I don't know. So yeah, the temperature is warmer down here, and this is the boundary of that. Free atmosphere. We talked about this. So in the free atmosphere, you only have pressure gradient force and Coriolis force. And the winds blow parallel to the isobars and the isohypses. So these lines of constant pressure and lines of constant height. So the wind's going to flow like this in between them. I don't know why it's gray. I wish it wasn't. Okay, we're going to get to it later. That's why it's gray. So don't look at that. Spoiler. Low pressure and height is always to the left of the direction of flow. They didn't clarify that. So you have this flow direction this way. To the left is where the low pressure is. To the left is where the low heights are. In the free atmosphere, again, only PGF and Coriolis, and the winds blow parallel to the isobar and isohypses. So this is the upper levels. Yeah, so you can see the winds. They're blowing along with these height lines. So these are height lines here. This is my website that I've been showing up. Google Pivotal Weather. You won't regret it. This is like the best website. Everybody will say to use other things, and I see what they mean. Everybody uses Tropical Tidbits or College of DuPage. Wonderful in their own. I'm biased towards Pivotal Weather because I had like 3 or 4 teachers use that, and so that's the only reason why I'm biased towards it. If you don't want to suck the data out of your phone, don't use it on mobile. But on the computer, big fan, love Pivotal Weather. So yeah, sorry, that was a tangent, but the low pressure is always to the left of motion. Yeah, so look, like you have your motion this way, and to the left relative to this motion, the heights decrease. The pressure decreases. In the boundary layer, we now have an extra force, and that extra force is the force of friction. So what does friction do? It slows down the wind. What does that mean? Coriolis is decreased. So winds are going to blow across isobars and isohypses, and they're going to be angled slightly to the left in the northern hemisphere. So the low pressure and height is always going to be to the left, but there's going to be this angled flow instead of having it be straight and parallel to these lines. There's going to be like more of an angle. It's angled slightly to the left. So here we go. You can see it now. These wind barbs are kind of starting to cross these lines. Like they're angled at these lines. They're kind of flowing with it, but it's not directly like before. Like let's look at before again. Look, like that's almost exactly parallel, but these ones have more of an angle towards the left. So the low pressure and the lower height is still going to be to the left of it. So it's still going to be this way, but there's more of an angle. When you have these lines closer together, we talked about this kind of, if you have height lines or pressure lines that are spaced closer together, you're going to have a stronger gradient. And that means that you have higher pressure gradient force, which means you have stronger winds. And this is true anywhere. This is true in the free atmosphere. This is true in the boundary layer. So let's look at this map again. You can see here the lines are kind of spaced apart. Okay, this is like what, I'm like 30 knots. Kind of slow for 300 millibars. But over here, like these lines are super tightly packed. What is that? 50, 100, 150, 155. The winds here are flowing at 155 miles per hour, as opposed to like 20 right here. So closer together, faster winds. Farther apart, slower winds. Yeah. Again, so this is what I like about Pivotal Weather. They put a big red where it's going faster. So slower around here, and they're kind of farther spaced out, faster right here, and they're closer together. Okay, I guess that's it for this week. So, not this week, this day, for day 1 of week 2. So this is lecture 6. Email with me if you have any questions. Reminder that your quiz is due on Wednesday at 11:59 p.m. It will cover lectures 1 through 5. It's not too difficult, but work by yourself. You can use your notes. I promise this quiz will not kill you. So, yeah, email me if you have any questions. And, yeah, I'll see you tomorrow.